Imagine a world where objects can vanish at will, a world where the visible becomes imperceptible and the impossible becomes reality. This is the tantalizing promise of metamaterials, a new frontier in science that is poised to revolutionize our understanding of light and its interactions with matter. These extraordinary materials, engineered with precision at the nanoscale, possess properties not found in nature. They hold the key to manipulating light in ways we once thought unimaginable, opening a portal to a realm where invisibility cloaks, perfect lenses, and other seemingly magical technologies could become commonplace. The very notion of invisibility has captivated the human imagination for centuries. From ancient myths to modern science fiction, the allure of disappearing from sight has fueled countless stories and sparked the ambitions of inventors and scientists alike. Now, with the advent of metamaterials, this once fanciful idea is inching closer to becoming a tangible reality. This is not merely an exercise in scientific curiosity. The implications of metamaterials extend far beyond the realm of laboratory experiments. They have the potential to reshape various fields from defense and security to medicine and communications, and fundamentally alter our perception of what is possible. The journey into the world of metamaterials is a journey into the very fabric of light itself. It is a quest to understand how light interacts with matter, and to harness this knowledge to bend, twist, and mold light to our will. Along this journey, we will uncover the secrets behind these extraordinary materials, explore their potential applications, and delve into the challenges that lie ahead in realizing the full potential of this groundbreaking technology. Welcome to the Invisible Revolution.
Metamaterials are not your everyday materials. They are not found in nature. They are meticulously designed and engineered. These materials are crafted from an assembly of tiny, repeating structures called unit cells. Each unit cell is typically much smaller than the wavelength of light it is designed to interact with. This sub-wavelength structuring is crucial, as it allows metamaterials to interact with light in ways that are impossible for naturally occurring materials. The prefix meta itself hints at the extraordinary nature of these materials. It signifies beyond or transcending, and that is precisely what metamaterials do. They transcend the limitations of conventional materials by deriving their properties not from their chemical composition alone, but from the precise arrangement of their artificial sub-wavelength structures. Think of it like building a house. The bricks themselves are important, but it is the architect's blueprint and the arrangement of those bricks that ultimately determine the shape, size, and functionality of the house. Similarly, the unique electromagnetic properties of metamaterials arise from the intricate design and arrangement of their constituent unit cells. This revolutionary approach to material science allows researchers to create materials with unprecedented control over their optical properties. By carefully tailoring the size, shape, and composition of the unit cells, they can manipulate the way metamaterials interact with electromagnetic waves, including visible light. This unprecedented level of control opens up a world of possibilities, allowing scientists to create materials that can bend, scatter, absorb, or even amplify light in ways that defy intuition and challenge our understanding of the natural world. Metamaterials are more than just a scientific curiosity. They are a testament to human ingenuity and our relentless pursuit of pushing the boundaries of what is possible. They represent a paradigm shift in the way we think about materials and their interaction with light, paving the way for a new era of technological advancements that were once relegated to the realm of science fiction.
Invisibility, once the stuff of myths and legends, is now within the grasp of scientific inquiry thanks to our understanding of how light behaves. To comprehend the science of invisibility, we must first delve into the fundamental nature of light itself. Light, in its simplest form, is an electromagnetic wave, a disturbance in the electric and magnetic fields that propagates through space. When light encounters an object, it interacts with the object's atoms and molecules, causing it to be reflected, absorbed, or transmitted. The way an object reflects or absorbs light determines its color and visibility. When we see an object, we are essentially perceiving the light that has bounced off it and reached our eyes. Invisibility, therefore, hinges on manipulating the path of light around an object, rendering it undetectable to our eyes or any other light-detecting device. This is where metamaterials come into play. Metamaterials, with their meticulously engineered structures, possess the remarkable ability to manipulate the path of light in unnatural ways. By carefully designing the unit cells within a metamaterial, scientists can control the material's refractive index, a measure of how much light bends when it passes from one medium to another. In essence, metamaterials can be engineered to have a negative refractive index, a property not found in any naturally occurring material. This negative refractive index is the key to achieving invisibility. When light passes through a metamaterial with a negative refractive index, it bends in the wrong direction, effectively flowing around an object concealed within the metamaterial, like water flowing around a rock in a stream. This bending of light prevents it from scattering off the object, rendering the object invisible to observers on the other side.
The concept of an invisibility cloak, once confined to the pages of science fiction novels, is now edging closer to reality, thanks to the groundbreaking potential of metamaterials. Imagine draping yourself in a cloak that bends light around you, rendering you invisible to the world. This is the tantalizing promise of metamaterial-based invisibility cloaks, a technology that has captured the imaginations of scientists and the public alike.
The basic principle behind metamaterial cloaking is deceptively simple. Guide light around an object as if it were not there. However, the engineering challenges involved in realizing this feat are anything but simple. Creating a metamaterial cloak requires an intricate dance of material science, nanotechnology, and electromagnetic theory.
One of the primary challenges lies in fabricating metamaterials with the precise structural properties needed to achieve the desired light-bending effects. The unit cells within the metamaterial must be meticulously designed and arranged to manipulate light at specific wavelengths and angles, ensuring that the cloak effectively renders the object invisible across a range of viewing angles.
Another significant hurdle is the development of flexible and adaptable metamaterials. Early prototypes of metamaterial cloaks were often rigid and bulky, limiting their practical applications. For a cloak to be truly effective, it needs to conform to the shape of the object it is concealing and adapt to dynamic environments. Researchers are actively exploring new materials and fabrication techniques to create metamaterials that are not only effective at bending light, but also flexible, lightweight, and durable enough for real-world applications.